on this, or it's not going to be very good. The variety of tables that you need, we're going to start to use the tables more, so you probably haven't had to go in there yet. But it has constants, it has tables, it has a solubility chart in there. There are more than one solubility chart. You're looking for one that is color-coded green and red. The other one is a series of solubility values. You can ignore that entirely. We will use that in Gen Chem 2. You have objectives due today, because it's Monday and we always do. The objectives due next Monday are going to be slid back 2 days to be due at the start of class on Wednesday the 13th. Wednesday the 13th is our midterm exam. I want to give you as much opportunity to study using ALEKS as possible, because the material we cover a week from today will be on the midterm, and basically we just moved the weekly objectives back 1 day, 2 days. They will be due at the start of class. You can finish all of them by Monday night. That will be fine too. It definitely doesn't say that yet. So like if you looked at it 10 seconds ago, it doesn't, because if I move the date and I don't tell you, you get stressed. So I'm telling you, and then I'm going to move the date. On Wednesday, we have a mini exam, which you probably knew. So it covers everything all the way back to percent yield, all of chapter 4, because we will finish that today. And then it looks like we will finish section 5.1, which is the first section in chapter 5, which I know you're like, oh my God, it's like a baby section. It's a small section. It has one calculation. Not even a hard calculation. It's a little hard. It's not the hardest. That's what it's on there. Don't forget the activity series video is important to watch. If you look at the activity series, metals can be oxidized by ions below them. That's the key. ALEKS will tell you, like, you may turn left if you go left. You may turn right if you go anti-left. You just memorize it one direction. That doesn't make any sense, but that's how I feel about what ALEKS says. Metals can be oxidized by ions below. Figure out the metal, and if the other one is below it, it happens. If it doesn't, it's in the opposite direction. So in the equation it's asking you for is the net ionic. So you just need to remove the spectating ion. We'll look at an example of that as we move forward, but I've gotten a bunch of emails about it. Questions about any of this information?
Can we possibly do some more practice like questions for all the stuff we covered? Or not all the stuff, some of them, like complete, and all that stuff.
I will highlight where they are available in class today. My best suggestion is there is a practice mini exam tomorrow. Mahi said she was waiting until lecture because she was like, if I send it out early and it doesn't have all the topics, you guys will stress out, which is fair. So it covers as far as we get today. So a lot of the chapter 4 topics are kind of sprinkled within everything else we're going to look at today. Any other questions? Mm-hmm.
It's more of a personal curiosity question, because we mostly deal with obvious things, but does the activity series chart also pertain to solid roll metals? So like would they still oxidize one another in direct contact if they were in the solid state?
Oh my God, what a great question.
I ask this because, like I mentioned previously, I work in construction, and one of my superior coworkers had mentioned to me as I'm still learning that you shouldn't place 2 different kinds of metals on top of one another because they may corrode over time. At least not bare metals. And so I figured that might be the same concept occurring.
I think, so the question is, if you put 2 metals together, do you get similar things? Was this in Florida?
This was in Florida, yes, but I'm just asking if they would oxidize one another, like in the solid state.
No, but water gets between them, and water can.
So if water gets between them, then the water oxidizes it.
I think basically one oxidizes into the water, and the other one oxidizes out of the water, usually, is how you can get that.
So basically it would be like condensation making it an aqueous reaction.
Mm-hmm. or more likely, so we don't tend to think a lot about acid rain, just because that, when I was in elementary school, they made it sound like that was going to be a big part of my life, like I should be very concerned about it. But acid rain is basically just like regular rain, because it's always acidic, or it's always slightly basic. So I thought like straight up acid was going to rain out of the sky, and that was garbage, turns out. So the slightly acidic or slightly basic moisture that you can encounter is what will start to run those reactions. Or if you have electrical current running through there, which shouldn't usually be happening on a construction site, but like hypothetically, if it did, that will push those reactions one way or the other.
So then, would it just still be the same oxidation occurring regardless of whether or not the metals were in contact with one another? Is it just the water that's oxidizing, or does the other material actually, interact?
I think, so the two metals, if you wiggle two metals next to each other, nothing will happen. If you have a facilitating ion, such as water, you can get indirect oxidation of both. Because you can get them both to change oxidation states, which I think is what you're thinking about. But sometimes I think that things happen in the chemistry behind them is perhaps outside of Gen Chem 1. I will look into that because that feels like an exciting topic. But as far as what the book tells me,
I just like applying real-world applications to concepts I learned because it helps me understand.
I would not take it to the bank that two metals sitting next to each other, just like a copper penny and a 10, I don't know what 10 is made out of, but like a 10 penny, together, nothing's going to happen. If you start to get water, acid rain, probably electrical currents, you can start to get other things. But in the absence of other environments, you should not get interactions.
You said there will be a practice exam available?
It's in SI, so in supplemental instruction. So typically on Tuesdays before the mini exam, she runs a review and practice session.
Those count fours are 2 SIs you have to be at for the year?
There is no mandatory supplemental instruction requirement. Not for my class, but there are in other courses. And there isn't. I would recommend that you go. If you would like to see your letter grade change, I would strongly encourage you to go. But if you are in math or physics, they have mandatory sessions that are not called SI. They're called, I don't know, PASS. PASS is one. And so there are some of those sessions. But there are no mandatory requirements for supplemental instruction in my course. Yeah?
What classes have these mandatory sessions? I took a lot of math classes.
Things, you may have taken them in the remote world, and things are a little bit different face-to-face. But I can only speak about my own class, and SI is recommended and encouraged, and all of the strong words of that, but never mandated. So, calendar issues. Now, depending on what calendar you looked at, it was right in some vicinity and wrong in other vicinities. On the last page of the syllabus, it had this really great graphic that told you everything you needed to know. Except, it said that the week after the midterm, so this all pertains to the next 3 weeks. Midterm exam in some places says that it's on the 15th, which is a Friday, and that's trash. We will be having it during class. It will definitely not be on Friday. So that due date was wrong on the homepage in Canvas, and it turns out on the front page of the syllabus. I'm probably in the middle of the syllabus where I listed out all the dates, because that's how I feel like this is going. The syllabus calendar in the back, so today we have class. Wednesday we have mini exam 3. Next week we have class on Monday, and then the midterm exam during class next Wednesday. The following week, so the 18th and 19th, are weather days, but we haven't actually had any, oh my God, hurricanes or any other reasons for school closure. So we will not be having class. I will not be here, so we're not having class no matter what. We can watch a video. If something happens, we'll watch a video. So those Monday and Tuesdays, there's no Gen Chem 1 or any other course. On Wednesday, which is the 20th, we do have class. But there's a typo in the calendar where it says we have class on the 21st. Basically, nothing changes if you didn't look at anything other than what I tell you in class. The important take-home message, if I had to give you like a tweet summary, we have class on Monday, Wednesday from 4:30 to 5:45. Anything that says it's outside of that is a mistake on my part. Questions about calendar life? UNF should be closed. Is Monday the 18th? On Monday the 18th, UNF is, as far as none of my classes are meeting. None of my friends' classes are meeting, which you cannot take that to some other faculty when you're like, you must not be her friend because. But the idea was that we held 2 days. So you know how in public school they'll have like weather days where like we could add school back to the calendar. That was the idea. Basically, because in many years we've had hurricanes and that's kind of like ruined everyone's life. So that's all that was. So basically we will have class if UNF is open. If UNF is closed, we will not have class. Other questions?
So it's more open there for the 18th, or we're not having class?
There should have, so UNF sends out like these Osprey announcements, which no one, I read them because they're full of like good nuggets. But as far as I am aware, they are non-instructional days, which means there's no classes. That there was a chance that those could turn into other things, but we haven't had a hurricane and we didn't all have to go home for COVID. So those were the 2 ways that we would have had class on those 2 days. But it is fall break. I will be out of town.
Is that just Monday or Monday to Wednesday?
Monday and Tuesday.
Oh, Monday and Tuesday.
Wednesday, we have school again. At least that's what my calendar, that's what my boss says, so. It should just be Monday and Tuesday of that week. So we'll take our midterm, you'll have 5 days to recover and spend your life away from here, 6 days, and then we will pick up with new material after that. Any other questions? Yeah?
On the Ionic, it says that there's a knowledge test or whatever.
Mm-hmm.
After we finish the part 4 and 5, that's for next week, right?
So the knowledge check should give you a good estimation of what it is that you know. So you just need to do those whenever you get to them. So your grade is determined by whether or not you completed I think it's 10 objectives. It should be roughly 10, depending on how you've done before this. If you finish those objectives, that's all you need. Other questions?
So if the next Alex objective is due Wednesday, will the following Alex objective be due that Monday or the following Monday?
You have objectives due tonight, and then nothing due until the 13th.
Okay.
So the ones next week, so you know it's due every Monday, those have moved back 48 hours.
And what about the following Monday?
That's like way far in the future. I think, so we go back to the every Monday, but not the Monday of, if I did the calendar right, which we now discussed my calendar issues. So it should be, if you look at it, there's like a long break. That should encounter fall break. And so then we will get the Wednesday, the 20th. So the next objectives after the 13th will be due whatever the Monday after that is. And it will cover the material on the 20th. And then we'll go back to the every Monday thing. Question? Yes.
The midterm, how much time are we going to take for the midterm?
You are given the full time. So it's 200 points, so it's basically 2 mini exams at once. Many of you, I feel like, are just coming to realize that. But the mini exams are half of what my exams used to be in the past. That's why they're called mini. So you give a 100-point exam, and then you have a 200-point cumulative exam on the 13th. Which, if we play our cards right, will cover chapters 1 through 5.
Are we going to have like a review for the midterm?
I would like to say yes, but we are way behind where I had predicted us to be. So it is if we finish early, yes. my estimation is that there will not be some, although I do have lots of office hours for people to come. There should be an SI mini exam review. I know that she said she was gonna start reviewing the earlier chapters. My recommendation would be to use the mini exams as a really great study template. So let's talk about titrations. So titrations basically have three phases. So a titration, step one is that we want to determine moles of known. Step two is we want to convert using equation the known to the unknown. And the third and final step is we want to, I don't really want to say do what the problem asks you to do, but that's really what it is. So we want to identify unknown, which could either be A, mass, or B, molarity. So when we think about a titration is typically an acid-base calculation where acids and bases are neutralized with one another. So in this case, what we have is we have the acid molecule and the base molecules, and at the equivalence point, they are even to one another. So we looked at this example on last Wednesday. And so in this case, it asks how many grams of calcium hydroxide. So at the end of the calculation, you would have identified the mass. So in this calculation, we are going to say one method to peel potatoes is to soak them in sodium hydroxide for a while and then remove the peel. The sodium hydroxide concentration ranges from 3 to 6 molar. In a solution analysis, titration, 45.7 mils of 0.5 molar sulfuric acid is required to neutralize 20 mils of a sodium hydroxide solution. What is the concentration of the sodium hydroxide solution? So the first thing we want to do, titrations have a known and an unknown. So the first step is to figure out what we know and what we don't know. The unknown is the unknown sodium hydroxide. So we know that there is 20 mils of that. And we know that the concentration of the known is 0.5 molar H2SO4, and we use 45.7 milliliters. So we've set all this up, but the first step in a titration is to determine the chemical reaction. So we need a balanced chemical equation. So we're going to take our sulfuric acid, which is H2SO4, plus sodium hydroxide. And this is just like a fancy metathesis reaction. We're going to swap our cations, and that gives us H2O plus sodium 2 sulfate, sodium sulfate. There are just two of them. So this is unbalanced. So we're going to drop 2 2s right here to balance that. So in this case, we have a balanced chemical equation. Now we can determine the moles of known. We're going to use the molarity and the volume in order to do that. So we're going to take our 0.0457 liters, multiply that by the molarity of 0.500 moles, in 1 liter of H2SO4, and that gives you 2.28 times 10 to the negative 2 moles of H2SO4. So this is step 1. Now we're going to take our 2.28 times 10 to the negative 2 moles of H2SO4. We are going to convert using the balanced chemical equation, just like we did in chapter 3 for like limiting reactants, if you remember back to that holy terror. So in this case, we know the moles of one reactant, we can convert to the moles of the other reactant. So for every 1 mole of H2SO4, we have 2 moles of NaOH. And that gives you 4.56 times 10 to the negative 2 moles of NaOH. This is part 2. Now we want to, in this question it says, what is the concentration? What are the units of concentration? Moles over liters, or molarity. So in step 3, we're going to take our 4.56 times 10 to the negative 2 moles of NaOH divided by 0.020 liters, and that gives us a final concentration of 2.28 molar. So what questions do we have about titrations? Yeah?
I'm just a little confused because up there it says the concentration ranges from 3 to 6 molar.
So this question used to have a follow-up that says, like, is this an acceptable version? So it's a process chemistry question. So it asks, so the follow-up question was, is this the correct concentration of sodium hydroxide to peel potatoes? But the answer to that question is no, because it is too low of a concentration. Yes?
Is this the same as dilution?
No. So the question is this the same as a dilution? A dilution is when you go from one concentration to a different concentration, but of the same compound. So students like to use M1V1 equals M2V2 here. In fact, some people teach that at other institutions. If you can follow the change in the molar ratio, that will work for you. Or you may take the one extra step to do the 3-step calculation as I've laid out here that will definitely get you to the right answer. I would recommend this pathway. Other questions? Yeah?
On the exam, will you take points off if instead of breaking it down into each step, we just did it all in one go?
Oh, no. I will not take off points for that. I try to set it up so that when you take notes and you come home and you're like, I don't know any of these things, you can at least follow the plan. If I were to write this on a key, I would have made one long equation. But this, well, maybe I'm wrong, but I think this helps us think about learning. So as long as you get this answer using calculations, I'm not overly particular on how you get there. Great question, though. Other questions? Okay. Another titration question. So a student finds a flask that contains hydrochloric acid at an unknown concentration. To determine the concentration, they titrate a 33.19 ml sample with 0.672 molar barium hydroxide solution. It took 22.97 milliliters of barium hydroxide to reach the equivalence point. What is the concentration of the acid sample? I'm going to give you 5 minutes to to definitely arrive at the correct answer. I will leave all of this work up. Yeah. Trying to take a shortcut, then I'll probably
This one, like the previous one, is at 2 to 1, and so this will always be 2 to 1. So, titration is basically the ability where we can measure when all of the acid is being consumed by all of the food. So, in my acid, you'll bring titration, and basically it'll add you for every acid molecule and every base will come together in water. So you're basically trying to get rid of either the acid or the base. You can think about it like that. Heater water, or whatever we call them, not like heater water. So this thing, if you wanted to put heat and rub to accelerate that, heat is molecular and we are not that kind of people. So you would have to come up with some ratio or to balance those, and you can do that using the balance. Yeah, if you are getting the same answer, I'm not too particular. If you're not using one of the only ones I'm doing too, I'm not too particular when I get there. Because there are different ways where you can sum together the numbers. So,
You're fine. Have an airport. Yeah.
22.97. Down here I used 33.19.
Yeah. Okay, so in this case, we are going to have a balanced chemical equation of barium hydroxide plus 2HCl gives us barium chloride plus plus 2H2O. So the trick, not a trick, but we need to note that 0.672 molar goes with the value of 22.97 milliliters, and there are 33.19 mils of our unknown HCl. So we're basically going to set this up pretty much the exact same way we did before. We're going to use the molarity and the volume to determine the moles. So we have 0.672 moles 1 liter multiplied by 0.02297 liters of barium hydroxide. For brevity, I'm going to go ahead and combine this. So 1 mole of barium hydroxide gives you 2 moles of HCl, and that gives you 0.0307798 moles of HCl. We're going to take our 0.0307798 moles divided by 0.03319 liters, and that should give you 0.927 molar. Some of you likely got 0.930, which is equally correct. Just has to do with how many of these excess digits you bring along or take away. But I'm a real people until I read all your answers, so if you're pretty close, you will get full credit. If you're not pretty close, you will get less credit. Question? Yes, ma'am.
I calculated the 33.19 with the 0.6277.
Did you get them backwards?
Yeah.
So the question, it's not a question, it's a statement. So did you get 1.4, give or take? No. So in this case, this is where partial credit is going to save you. Because I would give you a pretty substantial amount of partial credit if you did all of this, but swap these two things. Because in my opinion, you knew the more difficult part. You just got some type of the information confused.
How do you determine that? Because it says that the time period is 33.19 with, I think that's what it's going off.
So it says a 33.19 mil sample, which implies that it's the unknown. But the following line says it took 22.97 mils of barium hydroxide. So this is why I like to start with this graph over here, which if you assign them backwards, this graph doesn't actually help you, but it might assist you in these kind of situations. Titrations are scary because students try to skip some version of these steps in order to go from the problem to the answer as fast as possible. Make sure you have a balanced chemical equation. Make sure that you use the balanced chemical equation. More than likely, it will say, for full credit, you must have the balanced chemical equation, which is my way of saying, please use it. I try not to ask you to do calculations that are irrelevant. If I ask for the balanced chemical equation, you should use it. If I choose one of these that is not something you were required to learn, I will give you all of the information to acquire that, whether it's, so if we use like lactic acid or some other weird acid, citric acid, I will give you the chemical formula, the number of protons, and whatever the counterion is to help you figure out your balanced chemical equation. Questions? Please make sure you practice titrations. It will be on the mini exam. My current estimation is that it's worth 20%. But that's just because I wrote down some numbers.
The 0.672 is times by 0.2297, right?
Yes. So really just crummy multiplication sign. So let's spend a hot second and talk about oxidation reduction reactions, or redox. But mostly we are going to, if you have talked about redox reactions, they are very in-depth. It involves electrons moving around. It can get quite tedious trying to figure out where they go. We're going to do like a pass-by where we're going to look at these, we're going to look, and then we're going to move on. We're not going to spend a long time thinking about redox reactions. Mostly what we're going to think about is oxidation states. So an oxidation state is basically how many electrons have moved or are moving in terms of a metal. So when we think about reactions, and we haven't really talked about this, but the way chemical reactions work is we have a gain or loss of an electron. Maybe you got more electrons, maybe you lost your electrons, but that's how we make chemical bonds. Electrons will move around. So here in Florida, due to the high humidity and everything else, the silver tarnishes really bad. So I have silver jewelry that I basically have these little cloths that I polish before I wear it. And so the other thing is, if you leave your bike outside near the beach, it will get very rusty. I'm not saying I know this, I'm saying I know this. Your metal things, if you live out by the beach, everything rusts. It is due to the high salt content in the air, as well as just high humidity in Florida. So most of the time, oxidation reduction, like rust formation and other things, are pretty permanent, because you're changing the state of the metal. And so when we think about this, it allows us to think about oxidation reduction. So corrosion. So if we have zinc solid and we put it into bromic acid or hydrobromic acid, we're going to get zinc bromide and H2 gas. This is an oxidation reaction. So if we take our zinc solid plus 2 HBr aqueous, and that gives us zinc bromide aqueous plus H2 gas. What is the precipitate in this example? The H2. A precipitate in this case, typically we mean something solid, but it's basically anything that turns into a different state. So what is the spectating ion in this case? It's the bromine ion. So for the activity series questions, which this is basically similar to an activity series, in that case, it's looking at the reaction between zinc and hydrogen. So in this case, they're asking you for the net ionic equation, which would be zinc solid plus 2H plus aqueous goes to zinc 2 plus aqueous plus H2 gas. It's basically asking, where did the electrons go? So zinc solid loses 2 electrons to become zinc 2 plus. And we know that it becomes positive when it has lost electrons. And hydrogen H plus gains 2 electrons to become H2. So redox reactions that you may have heard about do these very intricate tracking of electrons. We are not going to do that. We are basically going to think about what it means to gain and lose electrons in terms of oxidation numbers. So oxidation is a metal or molecule that loses an electron. Reduction is a metal or molecule that gains an electron. These two things are tied together. One must gain and the other must lose. You can't just, everybody loses electrons. That's like not how science works. What we need is one to give up electrons and the other to take those electrons. So the oxidation number or state is effectively how many electrons any given atom has gained or lost in a reaction. Typically, you can calculate the oxidation numbers before and after and watch them change. For the most part, in terms of what we're really going to think about, we're going to think about what is the oxidation number of any element in a complex, which would be also important for this. So, oxidation numbers is a pattern. So is everything in this class. That's not helpful. When we assign oxidation numbers, we are looking for one element who is not following the rules. Everybody else follows these rules. So the first rule is an atom in its elemental form, so it's in a solid or a gas, or a liquid if it's mercury. But if it's by itself in its normal form, its oxidation number is 0. For a monatomic atom or ion, the oxidation number is equal to the ionic charge. Basically, do you remember how early in the semester we looked at our periodic table and we said aluminum is always +3 and selenium is always +2? That's basically what the oxidation number mostly always equals. Mostly it equals what you find in the periodic table. Nonmetals are usually negative, which is true when we think about what their charge is to make a molecule, right? Oxygen is -2, typically, if you're going to mix it with something else. Hydrogen gets a little crazy. It is +1 when bound to a nonmetal, and -1 when it's bound to a metal. Fluorine is always -1, and other halogens are mostly -1. I really like Sudoku puzzles. This is just that. It is basically I'm going to use all these context clues to solve for this one value. The hardest part is that people go, well, I don't know how to start. Oxidation numbers are always asking for a single element. Basically, what is the oxidation number of the unknown? Which we're going to look at some examples in a second. So you have to assume that everything else follows the rules for you to calculate about the unknown. So let's look at some examples. So in these 4 examples, and then we'll throw up another one, we are going to look at the oxidation numbers for sulfur in 4, soon to be 5 different conditions. So the easiest way to do this is to take our H2s, I don't feel like I meant to read this line at the bottom. So the sum of all oxidation numbers in a neutral compound is 0. They have to add up to whatever the molecular charge is. So if it's a polyatomic ion, the sum of these numbers has to equal the charge on the ion. This will make more sense as we move forward. Well, I think it does. So we want to know about sulfur and H2s. We, by default, are going to assume that hydrogen follows the rules. Hydrogen's rule is it's +1 unless it's stuck to a metal. Sulfur, not a metal. Great news. So we have +1 and +1. So when I write these out, it's basically the oxidation numbers per any atom. So there are 2 hydrogens, so there's +1 twice. What does sulfur have to be in order for it to be neutral? -2, +2. -2. Did you have a question?
No, I was going to say if sulfur was -1, and then you answered it.
Fair. If I tell you that sulfur 8 is its native state, what is the oxidation number?
In total or for the individual?
I will accept either one.
Shouldn't it still be -1 for the individual sulfur?
So the first rule is, if it's in its elemental form, oxidation number is always 0. So if sulfur 8 is the elemental form, whether it is sulfur 8 or a sulfur of the 8, what is the oxidation number? 0. I'm not going to ask you about something like sulfur 8 or like the many different states of carbon and ask you to determine their oxidation numbers. It would be like mercury, metal. Well, maybe not mercury. Cobalt, solid. That definitely is how you find it in nature. So up next, we have Scl2. Chlorides are -1. -1, -1. So sulfur in this case should be +2. You just add up the charges and figure out what it is on the other side, so that they add up to either 0 or whatever the charge is. None of these have charges. Questions thus far? Yeah.
Just to be clear, when you're talking about the charges, you're talking about like what we would get from the periodic table based on the column.
Yep. So, you know how we've talked about how the transition metals are the no rules kids? This is the part of the explanation for what makes them the no rules kids. So when we solve for them, which these are all about sulfur, more often than not you solve for the transition metals. And everybody else at the party has to follow the rules. You cannot solve for more than one thing at once. Do you have a question? Shoot. Oh. Thank you. I was like, I don't know where we're looking. I don't know where to put a 3. My bad. Yeah.
Sorry, I don't know if someone already asked this, but it's like, why is the chlorine -2 and the hydrogen on the first one is +2?
So chlorines are always negative, and hydrogen is positive unless it is combined with a metal. And sulfur is not a metal.
Based on where it is on the periodic.
Where it is on the periodic table, yeah.
So, like the sulfur over there, even though it has a -1 charge, it would change because of that metal, that non-metal. Like the H2s, I thought sulfur was a negative charge.
So it can be, but in this example, sulfur is the one that doesn't follow the rules. So what we're determining is it's been -2, 0, +2. This one is going to be something different too. So whatever is underlined does not follow the rules. So you have to assume that everybody else is what the charges are based on the periodic table. And those directly correspond with the oxidation numbers. So for this one, what do you get? +4. Some of you are very confident in that. For those of you who are still giving me the, I don't really know face. What questions do you have about assigning oxidation numbers? Yeah. So for this one, what is oxygen's oxidation number? So there's 3 -2s because there are 3 oxygens. Sodium's oxidation number is +1. And so when you sum these up, you have +2 and -6. And you need to have a +4 charge in order to make this a neutral molecule. So that gives you an oxidation number of +4. Other questions, oxidation numbers will get easier the more of these you do. The first 5 feel very uncomfortable, but they will get easier.
By neutral, you mean 0, right?
What?
By neutral, you mean 0?
Yes, neutral in this case means a charge of 0. Yeah. oxygen is -1 in peroxides, but I pretty much tried to remove peroxides from everything because I find that students struggle to figure out when is it peroxide and when is it something that looks like that. So that is the only time oxygen doesn't behave. And you would have to have context clues to know when it is. If I were to ask about that, I would have to name the compound. Because peroxide is O2, it's O2 2-. The thing is, rightfully so, you guys have a hard time figuring out when is it O2- and when is it like a hydroxide ion. So it is only a -1 when it is a peroxide, which is really rare to find, so we will not encounter those. Other questions? Excellent. Woo! Oh, man. So the activity series is part of the video online that you should have hopefully watched. In order to, don't forget, I will provide the activity series on the mini exam. Please do not memorize that. That will make you crazy. Metals are oxidized by the ions of metals below. Talk chapter 5. So for the time that remains today, I want to start to think about energy. So the reality is we have not explicitly talked about how reactions are done. I mean, I mentioned it earlier. I said you gain and lose electrons and things move around. But the reality is throughout most of the time we have spent this semester thinking about what is a balanced chemical reagent? What happens when you start with 5 grams? How much do you get? So today we want to start to think about, instead of thinking how much product do you make, how much energy is required to make that happen, or how much energy does it give off, and what is it relative to? So if you think about energy, it's kind of an abstract concept, but what we're going to start to realize is that energy is this ability to look at these reactions and say, this will produce 10 energies, and this other thing will produce less energy or more energy, and what are those relative to? So in this chapter, chapter 5, we're the first 2 sections, so we'll finish 5.1 today, and then we will start 5.2 on Wednesday. But 5.1 and 5.2 are going to build the groundwork. Then we're going to calculate enthalpy, which is basically how much heat or energy it takes to run a reaction. Then we are going to look at 3 different ways to calculate the change in enthalpy. Calorimetry, Hess's law, heats of formation. There is one additional method using bond energy, the energy of bonds, but we have not talked about a single bond, and so showing you that today would be silly. We will pick that up at the end of chapter 8, once we actually know what a bond is. So there are 4 ways that we can calculate delta H this semester. In chapter 5, now we will learn 3 of them. So, energy and thermodynamics. So, the study of energy is called thermodynamics. It's just a fancy word. It basically means the study of how heat and energy move around. And so, we're really going to think about how energy is converted into heat and work. So, when we think about energy, maybe you think about energy drinks. Maybe you think about electricity that comes out of the wall. That's really about all I got for you today. But we're going to think about it in terms of it's either heat or work. So if you were to pick up something heavy and you want to carry it somewhere else, you are going to expend energy to do work. You can also expend heat, probably by sweat, if you pick up something heavy and cart it over there. So work is the energy used to cause an object to move against a force. Basically, how hard is it to move this table from right here to way over there? That's how much work you're going to do. Heat is the energy used to cause the temperature of an object to increase. So when heat increases, the temperature goes up. When heat decreases, heat is going to leave the system, and so the temperature will go down. This doesn't really always correspond to how we think about heat in terms of like, how hot is it outside? But this will make the idea of sense as we move forward. So there are two energy units that we tend to use here in chemistry. We can use joules, which is Joules, which is if you were to want to write that out, it is 1 kilogram meter squared second squared. Most of the time, energy is provided in joules and will remain in joules. We're not going to do a lot of calculations where we convert out of joules into mass or the velocity. So calories is the non-SI unit. So when you go to the supermarket or to the vending machine, it tells you how many calories are in something you consume. That calories is actually calories with a big C, and it corresponds to a number of joules. So 1 calorie is 4.184 joules. And so if you have big calories, which is what you see on your like snacks, it basically is 1,000 calories, so it's in kilocalories. But this value corresponds to like how many calories your gummy bear is, or your apple, or whatever it is that you had for a snack today. So basically, thermodynamics is the study of energy. So in order to think about that, we want to think about different types of energy. So type 1 is kinetic energy, which is EK. This is the energy of motion. And so you could calculate EK is equal to 1/2 mv squared, where m is mass and v is velocity. So as the velocity increases, as does the kinetic energy. Potential energy is the stored energy. So we think about this as the energy in a spring. We can think about that in terms of energy stored in a complex. So a jack-in-the-box has a high potential energy because it's all compact, ready to expand whenever you finish cranking that spring. And the third part is electrostatic energy. So electrostatic energy is probably more important. We are almost never going to think about kinetic energy and potential energy this semester. We're going to think about electrostatic energy. So this is the interaction of two charged particles. And so opposite charges are attracted and have positive interactions. So E sub EL is equal to K Q1 Q2 over D, where K is the proportionality constant, and that is equal to 8.99 times 10 to the 9th joules meters over coulomb squared. Q is the charge. Typically the charge on the electron, which is 1.60 times 10 to the negative 19 coulombs. This is on an electron. And D is distance. All of the equations I give you guys today will be provided on the equation sheet, same with all of the constants. So the electrostatic energy is what's going to give rise to bonds. Bonds give rise to energy. Yeah? I'm sorry, come again? In the electrostatic? Ours is not, and that doesn't mean that it may be two different values. So when we think about electrostatic, this is basically going to allow us to determine how attracted or how repulsed two particles are. Our atoms are composed of protons, neutrons, and electrons. Protons and electrons are attracted to one another as one is positive and one is negative. Bonds are created by electrons, and so what we're trying to think about is how they interact with one another. So for the most part, we're not going to talk a lot about energy in terms of these calculations. We will calculate electrostatic energy later in the semester. But what are we really thinking about today? We're going to start to think about system and the surroundings. So the system is what we care about. The surroundings is not the system. So when we think about this, the way I like to think about it, we have a pot. We have some fire. If you are trying to boil water, I may blow your mind today if you don't tend to already know this, but if you want to boil water, it will boil faster if you put a lid on top of your pot. So if we put a lid on top, it is a closed system. This means that the energy does not freely distribute between the system and the surroundings. Basically, there is a hard boundary between what we care about, which is the water, and everything else. Open, closed system has a lid on it. An open system has no lid. Basically, when you boil a pot without a lid on it, the heat freely distributes from the water that you're trying to boil into the environment. That's why you can get kind of steamy above there or something else. So the system is what we care about. In this case, it is the water inside the pot. The surroundings is your kitchen, the fire, the noodles sitting by the counter, literally everything other than the water. And so as we think about this, it's going to allow us to discuss how the energy transmits between one and the other. So energy is, perhaps not shocking, the symbol for that is E. And the first law of thermodynamics states that the energy cannot be created or destroyed. So the internal energy E is the sum of all energy for a system. So basically, all of the energy everywhere is totaled as E. What we're going to want to start to think about today is the change in energy. But it turns out that energy is really hard to calculate in a single, infinite, or finite moment. It's hard to know how much energy is there now. What about now? What about now? But we can easily, or more easily, calculate the change in energy across time. The energy that you had this morning may be more or less than you have this afternoon. But how much energy do you have in this moment is hard to determine. You need a relative portion. So in that case, we can calculate delta E. This delta means change in energy, and it's E final minus E initial, which can also be thought of as after minus before. So how much energy do you have now, and how much did you start with? So I'll be honest. I spent a long time telling you that we can't calculate energy. And then I said, but we could subtract it, right? So the reality is that we need other data points to give us delta E. Because we still can't calculate E final or E initial. We are going to calculate the change in energy using heat and work. So delta E could also be calculated as Q plus W, where Q is heat and W is work. So the change in energy is equal to the heat plus the work, where heat is the energy transferred to warm a cold object, and work could be calculated as force times distance. On Wednesday, we will learn other calculations for work, because there are other ways other than force times distance. we will almost never calculate work using force by distance. It will be mostly provided as a value. It may shock you that while Q plus W feels quite trivial, there is in fact a complicated part of this. So if we think about our system, and we're thinking about the heat going in or out, it matters the relationship to the surroundings. So if the water is our system, when heat goes in, it's plus Q. So positive heat goes in. When the heat leaves, so if you boil water and then turn off the fire and leave it there, all of the heat transmits out to the surroundings. So the heat leaves the system, making it negative. For work done on the system by the surroundings is positive. Work done, if the system does work on the surroundings, work is negative. Delta E, the system gains energy when it's positive, and energy is lost to the surroundings when it's negative. I would strongly recommend when you work on your ALEX objectives to copy this table into something you can look at. Because it's not tricky. Tricky is not the right word. Part of the difficulty with this is it matters whether it says it's going into the system or into the surroundings. And every time you look at a problem, you're going to have to ask yourself, where's the heat going? Who is doing the work?
I have a question. What do you mean by work for the negative? The system does work on the surroundings. What does that mean?
So if you were to be doing an expansion in some type of a container that has a piston, as it expands, the piston pushes against the surroundings. So that is work done on the surroundings. Work done on the system would be if something is squashing the system. The heat one is very easy to think about. Work becomes, in my personal opinion, quite abstract. Because when I think about work, I think about running or something else. If you are looking for perhaps a different mental image to try to give you something, I think of work as gas in your car or whatever kind of vehicle you move around on that requires gas. In order to go somewhere, you have to put gas in the system. So that's plus, positive work. You put the gas in. And every time you drive somewhere, you spend gas. So that is work being done on the surroundings by the system. It's not the best analogy, but it's the best work that I think makes conceptual sense. So we'll start with perhaps there are two examples today. So this says, what is the change in energy for a system that releases 12.4 joules of heat to the surroundings and does 4.2 joules of work on the surroundings? So the reality is, we're going to do this calculation. Delta E equals Q plus W. Very, not simple, but kind of simple. So the question is, if we know that heat is 12.4, and we know that work equals 4.2, the hardest part of this calculation is deciding if it is negative or positive. So if the system releases heat to the surroundings, does that mean it is positive or negative? Negative. What about work? Also negative. So when we do delta E equals Q plus W, that is negative 12.4 plus negative 4.2, and that gives you negative 16.6 joules. So for the most part, if the calculation is set up like this, you should need to make sure that you are reading all of the words done on the system, by the system. Alex will switch it around every time and just kind of make sure you're hanging in there with them. So this is perhaps a slightly a more complex example. Gases A and B are confined within a cylinder and react to form solid C. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves down as the gases react to form a solid. As the volume of the gas decreases under the constant pressure to the under the constant atmospheric pressure, the surroundings do 480 joules of work on the system. What is the change in internal energy for the system? So for that one, it's the same thing where delta E equals Q plus W, where the heat is negative 1150 joules and the work is positive 480 joules. We don't need that line here. And that gives us negative 670 joules. You'll notice I put a positive sign in front of the ones that are positive. I do that for me. You don't need to do that. Numbers are assumed to be positive under all conditions. This is so that I know that I have finished deciding if it's positive or negative, just in case you see that annotation in some vicinity. Any other questions about, yeah? The mini exam stops with this calculation. So the titrations we talked about today and this, fair game. Say that again. This part will not be on the exam. I would learn. Yes. Okay. Yeah, guys, those will be present for you, but we will not be using those two powers. We will work equations with that in chapter. Yeah. I can try.